Hi, Kinesiology 3010. Welcome to our part 6 and our final lecture on inferential statistics. Okay, today we're going to talk about the one-way ANOVA. Okay, we're not going to do any mathematical calculations for the one-way ANOVA, but we need to understand the concepts behind it because it is one of the key statistical tests you'll see when you're reading research within the realm of kinesiology. Okay, so a one-way ANOVA is used for us to test the differences between the means of more than two groups or more than two different samples. So it's kind of like an independent t-test for 3+ groups. Okay, we can get more information that way. So the null hypothesis in this case is that population 1, 2, 3, and 4 are all the same, or there's no difference between means of any of the population. Okay. So we're saying that in our alternative hypothesis that at least one difference is occurring. So there is a difference somewhere between at least some of these populations or one of these populations between the others. So this is just testing to see if there is a difference at all. Is there one at all? So we're going to find this through looking at variance. Okay, we know that the ANOVA, I think back to ANOVA, analysis of variance, is taking into account the variance and where the variance is occurring. So we have our different types of variance. We need to find where that variance is occurring and why or if there's a difference in these groups because there is different forms of variation. Okay, so we're interested in the source of the variation between the groups. Okay, some of our information we need to remember: sum of squares is our SS, and then sum of squares is often or sometimes between or within, depending on the type of ANOVA. Sum of squares between groups or sum of squares within groups. So here's an example of when we would use an ANOVA. Okay, we want to know if the temperature if there's a significant difference between temperatures in the different samples or days. Okay, we want to know if temperature is different between treatment 1, treatment 2, and treatment 3. Okay, so in sample 1, we find our mean is 1, sample 2, mean is 4, sample 3, mean is 1. Okay, in sample 1, the treatment is 50 degrees, treatment 2, 70 degrees, treatment 3, 90 degrees. So did the temperature make a difference? Okay, there are 3 different conditions. Okay, temperature 1, 2, and 3 are 50, 70, and 90. And we're looking for the sources of variation in the values that we measured in each of these different conditions. So we want to know if the temperature or the treatment has a effect on the different groups. So we want to know, is there a difference occurring between the mean of 1, the mean of 4, the mean of 1? Here are the differences among the group. So there's 2 different sources of variance in this case. We have the variance between the groups. Okay, this is between group variation. Okay, so this is, say, due to the treatment, so between the groups. And then we also have variation within the group. Okay, this could be sometimes our error variation or sum of squares within, or variations within that group. So there's going to be variation between groups, and there's going to be variation within groups. The variation within groups comes from possibly error. Variation between is coming from, in our eyes, the treatment or what's going on, what our independent variable is doing. So there are sort of 2 sources of variation from the treatment and the error, or the sum of squares between, the sum of squares within. And we want to know if the difference is due to the treatment or if the differences are just errors. Similar to our t-test where we're comparing the difference to the standard error, we're looking as the variance of the variance due to the treatment there from the treatment or just from error. To do this, the ANOVA uses the F ratio, which is treatment effect plus differences due to chance divided by differences due to chance. We're not going to have to do any math with the ANOVA for this class, but just understand that our F ratio is determining how much the treatment effect is actually due to the treatment effect. So this F statistic is always right-tailored. It's always going to be a positive number. We're always directional. Yes, there is a difference, or no, there's no difference. There's no direction to is the difference less or more. The p-value is one tail only, but we haven't talked too much about tails, so don't worry here. So let's look at our ANOVA output. Okay, our ANOVA output tells us our sum of squares between groups, within groups, the total, the degrees of freedom between groups. So there's 3 groups, so there's only 3 degrees, or there's 2 degrees of freedom between groups. Within groups, we're looking at the total samples minus 3. We had 5 from each one, so we have n minus 1, n minus 1, n minus 1, and we end up with 12 here. And our F statistic is 11.25, and our significance level, or our p-value, is 0.002. That means that our p-value is 0.002, which is less than 0.05. So we would say there is a significant difference, or there is a significant ANOVA in this case. Okay, so in this case, there is a difference between groups, and that's all. That's all it tells us. Okay, and so let's use another example, a general example. So we have an instructor in a chemistry class, and they notice that the students that sit further away were more likely to miss class or use their cell phones during class. And he wanted to know if the students who sat closer to the front of the class did better on the exams. So he said, hey, there might be a difference between where people sit in class, and he wants to know if that actually has an effect on their exams. So he divided the chemistry classroom into front row, middle row, back row. And he's going to compare, do the ones in the front, the ones in the middle, and the ones in the back, are they different on their exams? So what statistical test should we use? Can we use a t-test? No, we can't use a t-test because a t-test is between 2 groups. In this case, he has 3 groups. So a t-test can only determine the difference between 2 groups. An ANOVA, what we're talking about now, can determine differences between more than 2 groups, 3 or more groups. So take that random sample from each group, take their scores from their exam. So here is all of our data that we've taken up from the front row students, middle row students, back row students. The null hypothesis is there's no significant difference in test scores among students who sit in the front, middle, and back rows. And our alpha level is going to be 0.05. And our research hypothesis is that there will be a significant difference between where the students sit and their test score. So let's look here at our summary of our statistics. So we have 7 students from the front, 9 from the middle, and 8 from the back. The mean score from the front is 75, the mean in the middle is 67, and the mean in the back is 53. Our standard deviations and our variance within the groups. So we're not going to do the math for the ANOVA, but we'll spend it through SPSS to get our output. Okay, SPSS is our statistical software that can perform these calculations for us. So we take our sum of squares, get our degrees of freedom, and we find our F statistic, which is 5.655, and our significance level is 0.011. What does that mean? There is or is not a significant difference. What do you think? That's right, there is a significant difference between 0.011 is less than 0.05. So our p-value is smaller than our alpha level. So we reject the null hypothesis, and there is a significant difference in mean scores of the front, middle, and back rows of the class. Okay, so what does that mean for our interpretation? All this tells us is that there is a difference between where the students sit and the scores on their exam. It does not tell us where the differences occur. Okay, so think about that. We know there's a difference, but what's actually different? Okay, we don't know from this ANOVA. We have to go further. Okay, ANOVA doesn't tell us that where those differences occur, and in order to find that information, we have to run what's called a post hoc test. And this is a test that we run after our ANOVA. Okay, so what is a post hoc test? A post hoc test is a test to determine where the differences are located, and we only perform a post hoc test if we find a significant ANOVA. If we find a significant ANOVA, we know there's a difference. Now we used a post hoc test to find the difference. The commonly used post hoc tests in kinesiology are the Bonferroni correction and Tukey's test, or Tukey's honest significant difference. These are the two tests that you'll probably see reading research in the field of kinesiology. So what we need to know about this is that our chance of making a type 1 error goes up or increases with the number of tests that we run. So the more often or the more tests that we perform, our chance of error just goes up from continuing to perform tests. In order to kind of control for that, a Bonferroni correction adjusts our alpha level or lowers the alpha level based on the sample size. So based on the amount of tests that we're running, it lowers our chance of type 1 error, which can in some cases be an overcorrection or a too conservative of a test, leading to a higher chance of a type 2 error. So it's good for reducing our chance of type 1, but that also gives us a higher chance of type 2. Tukey's test performs pairwise comparison, so compares 1 and 2, 1 and 3, 2 and 3, and pairs them up and compares them and determines the significant difference between those two groups. It doesn't do as much to correct for chances of making a type 1 error as we see with Bonferroni correction. But there is a better chance that we actually find a difference. So think of them as Bonferroni is a little bit more conservative. Tukey's test is a little bit more likely to find a difference. So we prefer to use the Bonferroni in more situations than Tukey's test because it's more robust, or it's more robust of a test compared to Tukey's honest significant difference. Okay, so here's a post hoc test. In this case, we have a Tukey's test, and we're comparing, in this case, the front and the middle, the front and the back, the middle and the front, the middle and the back, the front, the back, the middle. Here are our mean differences. Here are our standard errors and our significance levels from those tests. So let's look at the first one. We'll analyze the first one first. Okay, we're comparing the front to the middle, and our significance level is 0.389. From the front to the back, our significance level is 0.009. In this case, we have no significant difference between the front and the middle, but we see a significant difference between the front and the back. Okay, so there's our difference there. If we look at the next one, between the middle and the front, the middle and the back, if we look at our significance level, we see that there is a significance of 0.389, and from the middle to the back, 0.106. So in this case, there is no significant difference because neither of these values are less than 0.05. If we look at comparing the back to the front, just the same as comparing the front towards the back, we found that significant difference. So there is a significance difference between the students who sit in the front row and those who sit in the back row, but there's no significant difference between students who sit in the middle row and those who sit in the front and those who sit in the back rows. So those post hoc tests tell us exactly where those differences occur. The ANOVA just tells us that there is a difference. So ANOVA is our way to determine the difference between 3 or more groups. If we find a significant ANOVA, then we run a post hoc test to find where the differences are located. If we don't find a significant ANOVA, we're done. There's no significant difference. Okay, so it's kind of like a check the box. If we check it, then we go further. If we don't check it, then we're done right away. All right, so go through all of our lectures. This is the end of the content that will be covered on your exam or your midterm exam. So next week's lectures will be for your final exam. So just be aware of that. So everything up to this point is fair game for your midterm exam. All right, thank you very much and enjoy your weekend.